Since binomial random variables are discrete random variables, we talk about expected value again. So we actually have a formula we can use, again, just like for the previous modules. In this case, the expected value, again, for a binomial situation can be calculated by, right, the outcomes. How many outcomes would we expect to see under those conditions? Remember, the outcomes in this case are binary, either our success and failure. So the expected value, or the mean, right, the average number of times we would expect success would be n times p, right? The number of times you're doing something times the probability of success. So for example, in that Facebook problem we did earlier, if you asked 100 people, right, and we know 85% of them have Facebook, we would expect 85 people. That would be the average amount if we asked 100 people over and over again, n times p. Now, what would the standard deviation be of this variable if we looked at multiple groups of 100 or 50, right? It turns out to be, again, we don't need to know why. This is for mathematicians and for more advanced classes. Why the standard deviation in this case is the square root of n times p times q, but it is. And so keep that in mind. That's the formula for that. So let's say we have someone plays basketball, 70% chance of making a shot. John shoots it 20 times. What is the expected value? Now we're assuming it's a binomial random situation, right? N is 20, the probability of success is 70, and we're assuming, again, either make it or not. We're assuming there's independence between events, but again, it's an assumption, but in the real world, when people play basketball or sports, sometimes pressure gets to them. So there's other factors, but let's continue on anyways. You can see the simple calculation. 20 times 70 is 14. We expect him to make 14 out of 20 every time he shoots 20. Doesn't mean he will, it's just our expectation. Or the mean number that would occur over the long run, right? Thinking about what that means again. Standard deviation would be 2.5. So we expect him to make between 12 and 16 shots based on that standard deviation. We're going to see kind of a difference. Most of the, if he shoots it 20 times, we expect, again, in the long run, on average, you'd make 14, and the standard deviation would be 2.05. So again, if we let him shoot over and over 20 times, we would see between him making 12 and 16, because that's what that standard deviation kind of tells us. We use that standard deviation. Well, you know what? Let me show you one thing real quick on ArtoStat. So considering that situation, we're going to have John shoot 20 times. I'm in the binomial calculator again, binomial distribution, but this time I'm doing Explore. His probability of success is 70%. And what I like to see is, again, you see the probability table distribution here. Again, what's the probability that he would make 14 shots out of 20? It would be 19%. So you see the distribution. Can he make 20 out of 20? It's possible, but very unlikely. You see 0.008. But you start to see, you can look at these, the table that way also. And then notice you're given the mean and standard deviation. If you look over here at the top, you get the distribution, and then but you get the mean and standard deviation. So that's another way to do it. If you don't have access to that formula or you forget it, you could look at it right there from that. And then I like to then see the distribution and say, if he's a 70% shooter and he's shooting 20 shots, he's most likely to make 14, right? Because that's the average. That's why it's 19%. But it doesn't mean he's going to. Notice between 12 and that 16, there's a lot of chance within that. So it's with that we can answer that question too. And then we end this section on this question of unusual and what's likely, what do we expect? And so what we use is what's called the 2 standard deviation rule here. And here's the formula, the mean plus or minus that 2 standard deviations, right? Those symbols that we have here. Now, we like to have those values and that standard deviation because now we have some sense of the likelihood, like what would we see, right? So normally we would be okay or expect him to make 14, but we would basically say it's not unlikely, right, that he would make between 9.9 and 18. So like between 10 and 18 shots. If he makes that, that makes sense based on the probabilities and likelihood if you make it. Now, what would be unusual? Unusual would be anything below 9 and above 18. If that happened, we say, something's up. That was unusual, right? And then that would leads us to have to question the outcome or say maybe something else is going on. Maybe he's better, he's improved, right? Or he's gotten worse. If you start to see his numbers more often get past 18 or stay below 9, a change has happened. He's no longer the 70% shooter that we were assumed him to be. And again, that's how statistics will be used. And that's how we're going to use probability to evaluate scenarios and understand, or did we just see something unusual? Because if we did, then what's up, right? Did he get lucky, or fundamentally something's changed? He's a better or worse